So one method to get a white LED is you take a blue LED, a pump, or blue pump is what they call it, because it's the most consistent color control off the wafer in the manufacturing process, and then you put phosphor directly on it. In this case, this is what this is. This has a phosphor directly on the LED. This is a blue LED, believe it or not, and it changes it to that, whatever that lamp color, I think that's 4100.
4100.
Yeah, and so I'm blind here, I looked right at it. By putting phosphor directly on the LED, it causes it to run a little bit hotter. The warmer the color, in other words, if you want something more of an incandescent color, it takes more phosphor. So you can also get a little bit less light, and it causes the LED to run a little bit warmer.
So it would last less.
Last less, or you have to cool it off. You have to increase the current.
You got the fins, or
exactly right. You got to increase the current to get the same light output, and then now since it's running hotter, you got to add better.
And you're really overdriving it.
And you're overdriving it, which is permissible as long as you don't you don't exceed certain thresholds, like a junction temperature. Then the opposite is you take the same blue and you pull the phosphor directly off of it. Now I'm not encapsulating the heat directly on the LED. I can control how much phosphor and where it is, so that my wavelength out of here is going to be more consistent. And this will get me more lumens per watt delivered than if I have the phosphor directly on.
Now that piece that you have in your hand, that would come with different abilities to block different wavelengths.
That's exactly, or more phosphor, and that's
right.
Exactly right. Plus, this also actually has a material called meso-optic. Meso-optic is a holographic material. It was pioneered by Lidolite, which is a Philips company. And what we use meso-optic for, this luminaire here, is an architectural grade product. This is a 4-inch. This has 1,000 lumens out of the product.
Wow.
1,000 lumens. If you take a 26 watt lamp that's 1800, you get a 50% efficient optical system. You're getting 900 lumens delivered with 28 input watts. This is 27 input watts, and I'm getting 1,000 lumens. So I'm getting.
Okay.
So using that remote phosphor technology, I have a product here where I have a lot of casting. In here is my light engine. On the very back of this light engine, I have 16 LEDs. On the inside of this casting, it's built to a parabola, or to an angle, matching with the optics to get a medium distribution. I think this is a 1.1 spacing to mounting height ratio. I'd have to double check that. Lined on the inside of this is a highly reflective material by 3M called Vacuity, so that I can get as much light off of those LEDs out. And they're blue LEDs. I'm running it through a remote phosphor lens that also has a meso-optic material. There are 16 LEDs in here, 27 input watts. I'm getting 1,003 lumens out of this product, which is around 58 lumens per watt. It's a very nice warm color. Wow. This is the 3000K. Let's go back to that shadowing. We were worried about that multiple. Now see, you do have 16 LEDs, so you do have the shadowing. You have multiple point sources. Further you get away.
Right.
So anytime you have multiple LEDs, you have multiple point sources. That's just the nature of the beast. Okay. This is this one doesn't
Which
have.
is not good for you set
Statues.
Statues.
If you want to have, you try to control the shadows. This one I don't have the integral dimmer with it. My 6-inch actually does. This can dim down to 10%. It's a 0 to 10 volt control, so it's a violet and gray.
So I guess you have a problem with LED and landscape lighting with shadows effect.
Is that of a concern, landscape? You could, if it's multiple LEDs, you bet.
The only reason it would, well, on some things it wouldn't matter if you got a lot of leafy things, but on a tree, now you got multiple shadows.
Well, but again, it depends on
the mounting
the
distance.
spacing between the.
Yeah,
So
but
like what we did
landscape
here.
lighting's right up on it though.
Okay.
Yeah, but you're kind of shining up.
Right.
Now,
Grazing.
this is also built to the most current standards, which says that at 50,000 hours, actually I think this is 60,000 hours, at 60,000 hours, the light level will have dropped by 30%. So,
Right.
So what will happen?
So extend it because it's not directly on the bulb source at all.
Actually, this is right with what the industry average is. So at the end of, when I want to replace this, because I'm now below 70%, we build in the platform so that 50,000 hours from now, you just change this light engine. I always cheat a little bit. The first one's always the most difficult. This goes back to the factory. and you get a replacement. Instead of being 27 watts at 1,000 lumens, in 5 years it may only be 20 or 15 watts.
All right.
Yeah.
Okay.
So we built the future, the standard evolution of LEDs into this product, 4-inch, 6-inch.
All right. All right.
Now, Rick, when you're doing the LM70,
No.
you know, I guess the L70.
Oh, okay.
For the life rating, you're saying at 70% of its life, you'll have lost 30%.
No, we're saying at
I'm sorry.
50,000 hours.
Okay.
At 50,000 hours, we'll have lost 30% of
Okay,
the
you're saying
initial. elimination.
will have.
Right.
Is that a definite or?
Is that just a prediction?
That's what our testing shows based on using the chip manufacturer.
Yeah.
Have we run it for 50,000 hours? No.
Well, I'm just
Nobody
wondering
has.
if that's, again, based on like the tests that, 50% of the fixtures or lamps or whatever have reached that, and this is where you got, or is it an absolute that you will have lost 30% of light output from those LEDs at 50,000 hours, or could it be you still have more light?
Using the absolute photometry that we're required to use on the LM79 and the tabular data from the chip manufacturer LM80, the testing and the numbers say that at 50,000 hours it'll be 70%.